Chapter 1, Section 3, Part 2. We're going to look at multiplication, division, and simplification of fractions. And I referred to that other video a little bit. There's some tools to use in prime factorization, trees, and Venn diagramming. I have illustrated on a couple other videos. Might be good to review again with that. They also show basically here's prime factorization tree. We talked about that with 36. I can break that into 4 times 9, and then everything trees out from there. Notice that if I go across the lines the way they do this here, if I multiply, I could check everything should equal a product of 36. Well, multiplication of fractions is, again, to get used to this algebra language. I can say a lot with this algebra using expressions with variables, and in this case an equal sign. And the whole definition of how you multiply fractions is right in this equation right here. It says for any two fractions a and b and c and d, what you do is you multiply numerator times numerator. You get a times c here, and denominator times denominator, and you get this b times d. And hopefully by the end of this course or some other courses in algebra, you wouldn't even need really the English explanation for that. You should get familiar with how these expressions are really the language of algebra. Okay, and they'll start out with for any fractions right there. And a lot of times we're going to talk about division of 0 a few times too later on, where they'll have some restrictions on what numbers you can actually use. But there is a definition of how to multiply fractions. So let's look at example here. It says multiply 2/3 times 5/7. So according to our rule, we'd go 2 times 5, which is 10, and then 3 times 7, which is 21. And there would be our product of this multiplication. Now if we put variables in there, nothing changes again. And I think we tend to, when we have numbers in here, we've memorized some methods or had some things, and we're going to talk about cancelization and a whole bunch of kind of shortcut words and trying to find little knacky little English words to help you remember. I guess that's okay, but what we really need to focus in on these properties on why we can do some things. And they're setting this up. So this, even though there's variables in here, well, it's just denominator times denominator, which would be xy. And if I have a whole number, I can always easily write that as a fraction, and then I follow the rules. So 9 times 7/9, this example here, c, well, I need to write 9 as a fraction, which would be 9/1. There's actually an infinity ways I could write that fraction, but this is the simplest one. And then I have a numerator and I have a denominator to multiply, and I follow the rules. Now the next thing is a very important, very simple thing that, some of these early properties and laws we're going to talk about. You're saying, well, obviously I've known that since, a lot of times in first grade, right? So they're defining basically how to make a 1 here, because 1 is a very powerful number in multiplication. It's very easy to do. It's called the identity, and there's an infinity of ways I can write that 1. All I need to do is make sure that the numerator and denominator are the same number, as long as it's not 0. They put that except 0 there. So this is how to write 1 in fraction form, like I said. And they have to define that and say that it always works. Now here's some other words that we're going to talk about here that, I wish they would probably box this one. Reciprocals or multiplicative inverses. I kind of like this term multiplicative inverses because we're going to talk about additive inverses here in a little bit too. But these reciprocals are any two numbers whose product is 1. So how do I test to see if something is a reciprocal? I take this number times this other number, if the answer to that multiplication, the product, is 1, then they are reciprocals of each other. Or another word for that is multiplicative inverses. So the reciprocal of 2/3, in other words, what number can I multiply times 2/3 to get 1? And it would be 3/2. Because what I would get is numerator times numerator would give me basically the same number over the same number when I take the denominator too. So I get 6/6 or 1. And then we talk about a whole bunch of language about flippy things and flipping stuff and all kinds of stuff. But the definition of reciprocal is the number that I can multiply by this other number to get 1. That's the definition. So if I have a fraction, you can easily see that it's going to be the numerator and denominator will trade places, so I can get the same multiplication on the top and the bottom, right, or same product. Well, the reciprocal of 9 is 1/9. And a lot of times students will have a lot of problems until they see, 9 really is a fraction, 9/1. Oh, the reciprocal is 1/9, right? But also, if you think about reciprocals, what can I multiply times 9 to get 1? That's the definition. If I have 1/4, if I take the reciprocal of that, it would be 4/1, or 4, because 4 times 1/4 is 1. Okay, so they define these words, and again, anytime they name something in algebra, it's going to be important. And here's one of the first things that we use. It's very important to use reciprocals. Now we have rules for multiplying. So what do we do with division? So to divide two fractions, you multiply by the reciprocal of the divisor. Okay? So in these words of division, quotient means the answer to a division, right? The dividend is the first part, and it's divided by the divisor. That's this word divisor. So I need to take the reciprocal of just the divisor, the number it's being divided by, this fraction, and change it to its reciprocal and multiply. This is very powerful. In fact, division has a lot of problems with it because, the properties we've already covered, like commutative and associative, you cannot use those on division. You cannot change the order of a division and get the same result, and you cannot change the grouping in divisions and get the same result. But if I can change it to a multiplication, then I can use a commutative. I can change the order, I can change grouping, because that works on multiplication. That's just one of the many reasons to convert from division to multiplication. In fact, a lot of times when we get later on the course, I'll say, why use division? If you can use multiplication to do things, why not stay with multiplication? Because that gives me more opportunities to use these other laws. So let's look at this first example of division. So as I go through this, I'll say, well, I got 1/2 divided by 3/5. And what the first step should be then is to change this division into a multiplication, and then I follow the multiplication rules. So once I have multiplication, I multiply numerator times numerator, denominator times denominator. And then they bring in this identity property of 1, where the 1 is the identity of multiplication. Now again, this is probably something, that's not hard. 3 times 1 is 3. 17 times 1 is 17. Well, I can't prove things that way. I can't say, what about the next number? Isn't there another? There's an infinity of numbers that I can say. You can't prove something by just giving a few examples. And so they give us this property and say that this always works. That a times 1, any number a times 1 is equal to a, or in any order. I don't know why they have to put it in 2 order, because multiplication has a commutative property. We already have that covered, right? This is the multiplicative identity, or the identity of multiplication, is this number 1. Okay? Now we come back to this idea that, hey, I can write 1 in a lot of different ways. In this example, we can multiply 4/5 by 6/6 to find an expression equivalent to 4/5, or basically be the same value on a number line. And so when we do this, we basically can do this and prove that that's true, because 6/6 is equal to 1. We had a property for that. And 1 times anything is that same thing. So if we take 4/5 times 6/6, we'd end up with 24/30. This is not a simplified fraction, and we'll talk about what that means in a while too, but it also proves that these two things are equivalent. If I drew a number line and marked a dot on 4/5, and then I broke that line into 30ths, and I went 24 of those 30ths, I'd end up exactly in the same position on that number line. Okay? And in the reverse is where we usually work with this the most. If I think about this in reverse, if I started with 24/30ths, I can rewrite that fraction by pulling out fractions that are equal to 1. It's called simplifying the fraction. And what's really going on is we're taking factors of the numerator and factors of the denominator. And they don't show it this way, I would prime factor both to make sure I never miss anything. This first one they don't do this, the next one they do. But they say simplify, but what does that simplify mean? It means simplest form means that the only common factor between the numerator and the denominator is 1. Let me say that again. Common factors. Factors mean parts of a multiplication, so I want to break things into multiplication. Common means the same. So that's what they start doing. They say, well, if that's the definition, I should break these into factors, or parts of a multiplication, and make sure I know what's going on. So this first one here is 15/40. The factor 5 is a factor for both 15 and 40. But they show it this way, and I'm happy they do it this way. To show this, to say, well, 15 can be written as 3 times 5, and 40 could be written as 8 times 5. Now the rule about multiplying fractions, I can do that in reverse too. I say, hey, if it's numerator times numerator, and so on, I could come back and say, hey, I could break this into 2 fractions, and why do I do it this way? Because 5/5 is equal to 1. In other words, 3/8 times 1 is 3/8. So I pull out the common factors and make a fraction that's equal to 1, which simplifies my fraction. Now, definition of simplest form means the only common factor between the numerator and the denominator is 1. Well, the factors of 3 are 1 and 3. The factors of 8 are 2. They have 2 times 2 times 2 is 8, and 1 and 8, and 4, and so on, right? But if I use prime factors, it's just 2. So the only common one between those two is 1, because 1's always a factor. 1 times 3, 1 times 8, and so on. Well, that way they kind of grab the common factor. It happens to be prime, but the best way to do this, or the way to make sure you never miss any common factors that I can write as fractions equal to 1, is to prime factor them. So they took 36, they prime factored that. You could use those trees, and I get 2 times 2 times 3 times 3. And if you multiply that out, you'd get 36. If I had 24, I get 2 times 2 times 2 times 3. And what they're doing here is they're marking in red the common factors, and I could rewrite that in a different order. I can change the order with the commutative property because it's all multiplication, and then use the rule of fractions, multiplying fractions, and break this into 3/2 times this 12/12, really, or 2 times 2 times 3 over 2 times 2 times 3. Or I could say 1, 1, and 1, right? I could break that down. I don't even have to do that multiplication to figure out that that's equal to 1. And I end up with 3 halves times 1, or 3 halves, using the identity property. Now, really a lot of talk in here going through this. It's very crucial to understand why this works, because we can pull fractions out that are equal to 1. We can do this because I see a lot of students can reduce, they call it reducing, and reduce the fraction. I always kind of kid around in class. I say, well, what does that mean? Take 36 over 24 and I'm going to draw it smaller on the board? Is that what reducing means? And those kinds of things. We've had a lot of slang terms around there. What we're really doing is when we simplify, we're trying to get so the only common factor between the numerator and denominator is 1. They go through a couple cautions here, is that you cannot cancel into additions. This only works with factors and subtractions and stuff like that. When we get things like this, we usually don't see this with numbers, but 2 plus 3 over 2 sure doesn't equal 3. And this is one I throw on the board a lot of times. When I see this error in a test or something like that, if somebody asks the questions, I'll say it'll be like x plus 3 over x. When we get into more complex expressions and you're saying to me that that's equal to 3, well, let's throw 2 in for x and see if it works, right? I can substitute a 2 in there. Does 5 over 2 equal 3? And obviously it doesn't. So you can check these kind of cautions sometimes with doing a simpler problem and seeing if you're on the right track. It's tempting to do that, especially when you get variables in there to say, boy, that'd make this a lot simpler problem, you know, if I could just get rid of the denominator, okay? But they go through these cautions. These are very, very common errors. Pay attention to those, okay? So in this case, they simplify. They're just doing another simplification, and they're really kind of showing, you know, we could skip that prime factorization if you know, especially like this one. You got to remember that, hey, I can always take the factors of 9 as 1 and 9. A lot of times when we start doing this, you go, well, I got 9 over 9, but what do I put over that 8? Well, I really have a factor of 1 I can always use, and I get 1/8. I'll stop there.